Okay, so here we have the extreme value theorem, and this says that if we have a continuous function, so if f is continuous on a closed interval, a to b, then f will attain a maximum value so I should say absolute max. So an absolute maximum value and an absolute minimum. So unlike in that example we just saw of 1 over x, absolute absolute minimum. I should finish writing before I start speaking. And an absolute minimum value, right? So this is the extreme value theorem. So unlike that example that we saw of 1 over x, we do not have that a function like this will not have an absolute max or an absolute min. When I say attains, that means that it actually takes on a value, or there is a point in the closed interval where we plug it in and then f is equal to the absolute maximum value. So that's what I mean by attains. Okay, so these are a couple examples that just show that we need the hypotheses of the extreme value theorem. So the hypotheses are the things that we assume. So this statement, if all of this stuff happens, then we can make some conclusion. It's the if part, right? So our hypotheses are, first of all, that f is continuous and it's defined on a closed interval. So in this first example, we have a function drawn that is not continuous. So we see that there's this jump discontinuity, and so this function is not continuous. So let's write this down. And it does not have an absolute max. Because when we look at this is an open circle here, right? Since that is open, that means that the value of the function is not 3, even though it was approaching that from the left. It's actually down here. It looks like that's approximately 2. So that means that when we plug in this point, it looks like it's 1. When we plug in 1, we don't get that value that looks like it should be the absolute max. We get this value here, which is lower. And so this function does not attain a maximum value, so it doesn't have an absolute max. Okay, and then here is this next example has to do with the closed interval. So here we have a function that is defined on an open interval. So see that at the left-hand side of this interval, so this is a function defined on, well, the interval 0 to 2, but it does not include 0 because we have an open dot there. So it's actually defined on the open interval 0, and it also does not include 2 because we have a vertical asymptote there. So it is defined on an open interval instead of closed, which is, just to be very clear, which is open, not closed. It is continuous on this open interval, but that's not enough to make this conclusion that we make in the extreme value theorem. So see that this function has a vertical asymptote, So it will keep increasing and increasing and increasing, meaning that there's no absolute max or there's no maximum value that we'll reach, because it will just keep on moving past any finite number that we might choose to be our supposed absolute max. Okay, so there is no absolute max. Because there is a vertical asymptote at 2. And the function increases without bound. So increases all the way to infinity. So there's no absolute max. And also, there's no absolute min, and it's for a similar reason to this first example that we talked about, and it's because there is this open dot, meaning that the value of the function, it was decreasing all the way to this point. It was approaching 1, but it did not actually reach it, so it did not actually attain that minimum value. So there's no absolute min because the function does not reach 1. So the supposed minimum value that we would think it would have. Okay, so these two examples show us that we really do need both of these hypotheses. And so right, this is the extreme value theorem, and we will have some other results in this section, but we're not going to complete this whole section. So we're stopping here, and then we'll continue with this in the next set of videos. Okay.